We are starting chapter 3 today, which is continuing on with our second topic of derivatives. And taking out derivatives and applying them. That's the reason it's called derivatives. Makes perfect sense. Today in particular, we'll be talking about something called Extrema. That is a plural. You gotta do that right now? You won't dehydrate in the next couple minutes, right? Yeah. Okay. So it would be fun if you did. The organ shut down and everything else. So we're going to start by defining what extrema are. Go ahead. We're going to talk about the difference between relative extrema and absolute extrema. That'll come later. We'll talk about the difference between doing it on an open interval and a closed interval, meaning including the endpoints and not including the endpoints. And of course, you should be able to snap your fingers.
I can't.
Really?
I can't. I like.
Can anybody else not?
Use your middle finger. Or no, use your.
So maybe do one more.
Your ring finger. Yeah.
You really can't snap your fingers? Okay, it happens. It's all right. It's like I can't do that tongue thing, that roll tongue thing.
Like when you want.
No, just like this, I can't do that.
Like what? Well, that's genetic.
You can what?
No. Wait, no, wait a minute.
Don't do that again. Oh. I don't want to talk about it. No! Don't encourage her behavior. No.
I want to know what not to do if you don't know it.
Dude, this is.
We have something called a minimum and a maximum of a function f on an interval I. So there's a lot of verbiage in there that you need to get comfortable with because we'll be using that verbiage quite a bit. The minimum and the maximum are what's called extrema, or extreme values. We're going to start by talking about absolute minima. That's the plural of minimum. One of them is a minimum. More than one is a minima. And absolute maximum. The plural of maximum is maximum. However, some sources also use the term global to mean absolute. So don't freak out if you see global, because global and absolute are the same thing, meaning the entire graph. Because later we're going to have to transition that into what's called relative extrema, and it's going to get a little confusing. But we'll talk about absolute first. So f of c is a maximum of f on I being the interval, if f of c is less than all the other x's. That's a fancy way of saying c is the low point of the graph. Step 2, it's a maximum if that c value, f of c, remember we talk about a point, if the x value is c, the y value is f of c. And so if that y value is the biggest y value on the whole graph, then that becomes a maximum. And we'll use a lot of other terms for that, like peaks and valleys, and hills and valleys, and all that other fun stuff. Okay, good? Did you do any of this last year at all? No? Good. All right, this will be fun. Okay, that's what I just said. Okay, maximum is the biggest value, minimum is the smallest value. Over the entire graph, because we're talking about absolutes, and which is the same thing as globals. So if we look at the left graph, I have a closed interval, meaning I'm including the endpoints. So if I look at the bottom of that parabola looking thing, that would be the minimum. Why is that? You scared me. What are you, a ninja or something? Don't sneak up on me like that anymore. No está aquí. Right? Español, sí? Sí, bueno. Gracias. Adiós. Where was I?
Spain.
I was speaking Spanish, yes, but before that.
Did you teach a whole
You told her anything?
No. There's no way.
You ever tried?
No.
You don't have to
Do you want to try?
Yeah, that's what I'm saying.
Don't go to me. Because it would quickly resolve into Spanglish where I just been making, yeah. Botto does nato para el maximomo. Yeah, we're not going to go there. Where was I? On the left picture. The bottom point of that is the minimum, because obviously if you look at that picture, it's the lowest point on the graph. And then if you go all the way to the right, like it says, there's a maximum over there. That's the highest point on the graph. Fairly easy concept, yes? Good. Look at the right, however. Same minimum, but now we're doing it on an open interval, meaning we're not including the endpoints. And so now we get into some philosophical stuff. How close can you get to that point? That point, by the way, is at 2, 5. How close can you get to 2, 5? Infinitely close, correct. Therefore, since you can continue to get closer and closer and closer and closer and never get to it, this has no maximum. Okay, there is no highest point, which is kind of a weird concept for some people to wrap their heads around. In this case, there's a minimum, but no maximum, because you're not including the endpoint, which happens to be the highest point.
So, what would you rate the answer?
No maximum.
There's no.
Right. El maximum no está aquí para
See.
L function? La function?
La function.
La function? It rolls off the tongue more, doesn't it?
Función.
Yeah, función. La función.
There it is.
That sounds sexy. Bueno. By the way, I've converted from PowerPoint to Keynote, and I can't decide on what transition I like, so I just chose all of them. So we'll be. I would respect your input on to I would respect your input about the transitions from slide to slide.
First one.
You like the first one? Ready? Well, hold on. There's a lot. I got a lot of slides. Question?
Just keep surprising us. Like, just throw in different ones everywhere. Just
every
yes,
one in
Can you handle the randomness?
I don't think I can.
We have
Only
so
one
far.
way to find
I'm not a very random person. I'm fairly structured, so we'll see if I can cope with that. Okay, so there's the concept. Finding the highest point and the lowest part of the functions. Now we get into the mechanics of how to do that. All right.
That was very deceiving because it went to the left.
Oh, yeah.
That's very true. That's true.
So let's not put our vote in for the confetti yet, because you haven't seen what else I got in store for you.
That's so.
You
Wait,
raised the
I was the
bar,
first one.
like,
It made me
you said
feel
it
about
was
going
like
back to
three
the
months.
previous slides because it went to the left.
Yeah, I didn't like it going to the left.
I did not like that.
Okay, thank you. Appreciate the input. All right, so now I've got a function. It's a cubic function. Who cares? There's a picture in case you care. I don't. But anyways, now we switch our terminology into relative max and relative min. So remember way back when we talked about neighborhoods? Yeah, thank you. I knew somebody would say it, right? Worst day of my life. We're going to be looking at neighborhoods now. Are you okay?
Yeah, I'm good. Just swallowed my gum accidentally.
That's outstanding. That would have been great if you would have just started choking. Just because I've never had that happen before. Okay? Anyway, stop sidetracking me. Relative max and relative min means the highest point on a small chunk of the graph. So notice if I look at this graph, this point right here we would consider a relative maximum because it's the highest point in that little area there. However, if I come all the way over here, these points are higher. So this is a relative max, but not an absolute max. Same thing is true down here. This is a relative minimum because it's the lowest point in that little neighborhood over here. But it's not the absolute minimum because if I continue down the graph, I get lower values. And if you consider the fact that this cubic extends up forever and ever and down forever and ever, it would have no absolute max, nor would it have an absolute min, but it does have a couple relative maxes and relative mins. Our goal is going to be to find those relative maxes and mins, and the process is fairly easy once we answer Jim's question.
So if you say that it's got a relative maximum at blank and a relative minimum, wherever, don't you have to specify the neighborhood for that then?
No.
Why?
No, because the assumption is that we're getting a fairly small area. enough to function, and nothing else weird is happening in that area. Could we find a function that's oscillating like crazy in that little region and everything goes to hell in a handbasket? Yes, but we don't. That's,
Okay.
those are few and far between. All right, we good? All right, everybody ready? Again, I'm just throwing them in there.
Can you do it again?
Just, no,
Use that one before though? Are you sure?
no.
Oh, it's been the sixth.
Did the drop it. Okay. This is the fancy definition of the relative extrema, so relative max and relative min. Okay? In the open interval C, blah, 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 blah. Now, here's to make things even worse. So we've got absolute max and min, which is also known as global max and min, right? Yeah, good. Now we have relative max and min, which are also sometimes called local max and min, because somebody can't make up their mind. Hey, personally, I like global and local better, but that's not the most common terminology. The most common is absolute and relative. Okay, ready? Again, I'm just throwing it out there.
You seem pretty excited about that one.
That one? No, I just wanted to make sure everybody saw it so that I don't have to go back. I didn't see it, go back.
It's evidence that was relative.
Yep. All right, so looking at part A. Find the value of the derivative at each of the extrema. Here's a little function there. It's got a little hill there. And on top of that hill is a relative maximum. We don't know what happens to this graph as it continues on to the right, but let's assume that this graph continues to be, let's say it's asymptotic to the x-axis. Are you okay with that terminology? Okay, good. Notice that that point is not only a relative max, but it's also an absolute max. That's the highest point on the graph. Okay. What about a relative or an absolute minimum on part A? Are there any? If so, where are they? Doesn't look to be any on that graph, right? So it's possible that of those four, you could have pretty much any combination of those four things. A relative max, an absolute max, a relative min, an absolute min. Basic sine graph. Okay. And this is where we start talking about the neighborhood. So we have a period of the sine graph where it goes up and down and up and down and up and down. This point here, pi over 2 comma 1, is a relative max. Where's the absolute max on that graph? Who said that? You?
Yeah.
Why?
Because it's the same maximum at every point.
Good. Okay, it would seem like this would also be an absolute max, but recall that the sine graph is periodic, so it continues to repeat. So I'd have another relative max over here that would have the same value. You can only have one absolute max or min. And so since the value repeats, it has no absolute max and min. It does have relative max and mins. Now, we still need to answer the question. Find the value of the derivative of each of the relative extrema. All right, so let's start with, let's do B first. And we'll talk about this point here. So take the derivative of sine, which is cosine, plug in pi over 2, what do you get? 0. Take the derivative of sine to get cosine, plug in 3 pi over 2, what do you get? 0. Come over here. Take the derivative of this function. How would you do that, by the way? 2 ways.
Bring the x to the third power up.
Okay, sorry, 3 ways. Bring the x to the third power up, turn it into x to the negative third product rule. Good, 1 way.
Quotient rule.
Quotient rule 2. Nope.
Could you multiply the 9 and then do the
Good, and then what?
and then do the quotient?
Yikes.
Oh. It's the worst transit. How does it
Yeah?
How does it stay?
Magic.
No, from like ship A.
What did you just say?
That was like so long.
Did it sound like he swore?
No, like ship A to ship B, like how that was so long ago, like how that stayed.
Because I haven't used it since then. Third way would be to split the fraction. 9x squared over x cubed minus 3 over x cubed, which gives me 9x to the negative first minus 3x to the negative third, and go from there.
Why would
Okay.
you multiply the 9 with 3?
Oh, I should, yes, thank you. 27. Thank you. Okay, so 3 different ways to do the same thing. It doesn't matter what you do, but what do you, and we're not going to do it because hopefully if you're good at pattern recognition, what are you going to find out about the value of the derivative at that point?
0.
0.
Why?
Because it's
You want to just go with it? Does everybody agree that it would be 0? The question was, we came over here and we took the derivative of sine to get cosine, plugged in pi over 2, got 0. Plugged in 3 pi over 2, got 0. And my question was, well, if we went through the hassle of taking the derivative of that bad boy and plugged in, what does that say, 3, what would we get? And Oliver's suggestion was that we would get 0. And then I asked him why, and he froze up on me. Which is understandable because we haven't really talked about why you would get 0.
Isn't it?
Because what?
Answered on the bottom.
Because the answer's right there on the bottom. What Kate said.
Was that actually the answer you were looking for?
No.
Wait, why isn't it?
What was the answer you were looking
Yeah.
Is it because you take?
Well, here, we'll get to it.
Is it 'cause you take?
Take the derivative, I did quotient rule, plug it in, blah, 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 you get 0. Okay, so that confirms what we already suspected, is that without doing the work, there's the derivative at that maximum equaling 0. So it's not a fluke that we looked at 2 relative maxima and 1 relative minima and put in the values at each of those points into the derivative and we got 0 every time. It's also not a fluke that one of the questions you've been asked over and over again is, where is the derivative equal to 0? So now we start fitting puzzle pieces together. Why do we care where the derivative equals 0? What happens when the derivative is equal to 0? Before we covered this, yes. What else happens when the derivative is equal to 0?
Tangent.
Who's talking? Kate?
I said tangent line.
What about the tangent line?
I said it's horizontal. Yeah, horizontal.
Good, it's a horizontal tangent line. Okay, so look back at this picture. Whoops.
Why did you take the derivative of 3 and not the derivative of 5 and 2?
Because that applied to the first problem. If I draw a tangent line to this sine graph at that hill, I'm going to get a horizontal tangent line. Put it at the valley, I'm going to get a horizontal tangent line. Put it at this maximum over here, I'm going to get a horizontal tangent line. So the horizontal tangent line thing keeps popping up over and over again, and that's actually when we get into the calculation stuff, what we're going to use to find these extrema. I did that one too. Okay, we did this one already. Great. Yeah, click. Ooh. Whoa.
good.
What happened? There we go. Must have hit it twice. Okay, so we found some relative extrema. Now, where did those relative extrema come from? From those points, so we're going backwards now. We already knew where the function had a max or a min, and we plugged those into the derivative to get 0. Now we're going to go the other way around. We're going to take the derivative, set it equal to 0, and find out where those things happen. Those spots where they could possibly happen are called critical numbers. Critical numbers are where the derivative equals 0. 2 ways that you can get a critical number, and you have to remember this. One way is where the derivative equals 0. The second way is where the derivative is undefined. Okay? So here's an example where it's equal to 0, horizontal tangent line. Here's an example where it does not exist. We have a cusp.
Does that go along with the whole like can of corners thing?
So you might have a corner, and that corner could be a max or a min, we don't know. And we'll,
So you just say doesn't exist.
correct. The derivative doesn't exist, which means it could be a critical number. Okay. Once you find the critical number of a function, that critical number might be a relative max or a min. Now we go back to some geometry, you know, when we talk about the logic here. If something is a critical number, doesn't necessarily mean that it's a max or a min. Okay? If something is a max or a min, it must be a critical number, but the converse is not true. That might have confused some of you, but I'll explain in a second.
If it doesn't exist, then it could be a critical number. But it's not.
Correct, but doesn't have to be. Okay? Which is what that says. If f prime of c equals 0 or is not differentiable at c, then c is a critical number. Okay? That's the fancy definition of what we've already said, the two ways to get a critical number. And as I said, this is big. There's also what I was talking about. If you have a relative max or a relative min, those values must have come from critical numbers. So all relative max and mins are critical numbers, but not all critical numbers are maxes and mins. And eventually we're going to get into some examples of where you put this into practice. And actually the practice of this is not too bad, because you've all become masters at taking derivatives. Okay, we good?
Hold on.
Okay.
That was trippy.
Yeah. All right, so here's the process we're going to use. First of all, find the critical numbers. So how do you find the critical numbers? Take the derivative, set it equal to 0. Next thing you're going to do, that'll tell you the x values of all those critical numbers. Then you're going to find the y values of all those critical numbers. How do you find the y values? Plug it back into the function. Step 3 is the one that everybody forgets about. You have to include the endpoints. Because notice it says we're finding absolute extrema.
What if there's not an endpoint?
Then you can't plug it in. Yeah, so you just plug in the endpoints as you know. But we're doing it on a closed interval, which means you have the endpoints. And this will make a little bit more sense once we start doing an example here. So now you got all this stuff. You found some critical numbers. Let's say the function has 2 critical numbers, and it's got 2 endpoints. So now you got 4 things to test. You find out the y values. You've got a list of numbers then. The biggest number is the maximum. The smallest number is the minimum. The other things are just stuff. They might be relative maxes. They might be relative mins, but we don't care because we're just focusing on absolute extrema right now. Okay, we good? Yeah. Good. All right, so
Yeah.
all right. All right, so let's do this. Got a function. It's a quartic. I have no idea what it looks like, nor do I care at this point. We'll care about that later. And we want to find the absolute extrema from -1 to 2. Step 1. Take the derivative, set it equal to 0, find the critical points. A lot going on there. But for the first one, I chose a nice easy function that you should be able to take the derivative of easily and solve that. In case you can't, there's the derivative. Whoa, there's the derivative, which I set equal to 0 and solve. Now how do I solve that? how do I solve that?
Factor out.
GCF? Factor out a GCF, and therefore my critical numbers are, and 0, good. Critical numbers, which you'll probably get in the habit of abbreviating as CN. Capital C, capital N. Okay, I don't know what step we're on there. So we found the critical numbers, good. So now we're in step 2, evaluate the critical numbers. So if my critical number happens at x equals 0, I'd like to know what the y value of that critical number is so I know how high or how low it is. How do I find those? Plug it in. You might want to bust out your calculators, by the way, just to make your life a little bit easier. There's a couple different ways you could do it. I mean, the function wasn't that tough. You could probably do it in your head. Or you could use a table. Or you could just plug and chug into your calculator. It's entirely up to you. Or you could use, no, those are pretty much the best ways to do it. I don't even remember what the function was. What was that? Oh, hold on.
3x to the 4th minus 4x
Whoops.
to the 3rd.
Oh boy, 3x to the 4th. So if I put in 0 there, I get 0. That's okay, that's not bad. And then if I put in 1, negative what?
1.
Negative 1. Because you come to these are critical number. Okay, by the time. Okay, so then what I did is I organized a nice little chart here. Here's the negative 1. There, nope, sorry. There's the 1 and the 0 that we used already. So we got the 0 and the negative 1. But then since we're looking for an absolute and it's a closed interval, I have to test the endpoints. And it said in the original problem that it was on the interval from negative 1 to 2. So if I figure out what f of negative 1 is, I end up with 7. And if I figure out what f of 2 is, I get 16. Don't overthink it from this point on. You simply look for the biggest value. And remember, we're looking for y values here because we want to know how high up or down it is. The biggest value is 16, so that makes an absolute maximum at 2. The smallest value is negative 1, so that puts a absolute minimum at negative 1. Question?
For the right endpoint and left endpoint, what do you plug negative 1 and 2 into?
The original function.
The 3x.
Oh, okay.
3x to the 4th minus 4x cubed. Yeah, because you want to. Everything's dealing with the original function, so we want to know how high up or down that original function is. Mark.
Wait, so we plug the 0 and the 1 in, and then we plug
The 2 endpoints.
the same thing?
Yep. Yep. They all go in the same thing. That's why using your calculator will make things a little bit easier. You create a table, do whatever you want to do to get those numbers. Or, like in this case, it's not that difficult to plug and chug.
They all go back into the original? Okay.
Yeah. Okay, understand the concept?
It doesn't need to be the minimum and maximum could be an endpoint and a critical number. doesn't it?
Yep. It could do all kinds of weird different things. Your max and min might be the 2 endpoints, and you ignore the critical numbers. It could be the 2 critical numbers represent a max and a min, and the endpoints mean nothing.
If you get the same answer for an endpoint and a critical number.
Great question. Did everybody hear that question? Ask it again louder.
If you get the same answer for the endpoint and a critical number, does that make them both the max? Or
I'm going to answer your question by referring back to what we talked about on the sine graph. Did we have an absolute max on that sine graph?
relative max?
We had relative maxes, but not absolute. Absolute, you can only have one of them.
Okay.
So if these two ended up both being 16, no absolute max. Okay? All right, we good so far? So now, critical numbers need. Okay, we talked about that already. That doesn't need to produce a max or a min. All right, let's have some fun. Find the critical numbers of that bad boy. That's all you got to do. Just find the critical numbers. We'll worry about whether the absolute maxes and mins and all that other garbage later, but just as a little practice here, see if you can find the critical numbers for that bad boy. This also fits another piece of the puzzle together. Remember when we were doing, I'm just going to talk while you're working. We were doing problems and I said, no, we don't want them to be sums or differences, we want them to be products. And that's why we factor things out. It becomes relevant in a problem like this. When we want to start looking for absolute and relative maxes and mins, we want it to be a series of a product, which allows us to have an easier time finding the critical numbers. Hopefully you're doing some product rule. Maybe a little chain rule mixed in there. Actually, chain rule doesn't become relevant in this problem because I chose linear function. But if the function was uglier, you would need a chain rule. Eventually what we're going to be working towards is taking an ugly function like this and being able to graph it without using a calculator. Using our vast stores of algebraic and calculus knowledge, we would be able to put together, or I should say we will be able to put together a fairly decent graph of that extremely weird function. Anybody know what time the period's over? 40? 40? Oh, okay, we're doing all right. This is the last thing we're doing. Should be done. Okay, so you got a couple things going on as you're doing this. Number one, you've got the calculus. Can I take the derivative of that bad boy? The second thing is, okay, now I've taken the derivative. Can I set that monster equal to 0 and figure out what the heck the values are? Both are crucially important. Yeah, don't multiply them, don't. I'll show you one. I'll do it. Anybody got them yet? Anybody think they're going to be able to get them, or should I just start doing it? Start doing it. Okay. Product rule, right? All right. So f prime of x is equal to 2 times x plus 7. Reduce the power by 1. Chain on the derivative of that, but the derivative of that is 1, so I don't care. Times a second. Plus the first. Times the derivative of the second. 1/3 times x minus 8 raised to the negative 2/3 power. Chain on the derivative of that, which again is 1. Okay, so far? Some of you look like you're going to throw up. We're okay? Now, this is what I talked about before. This is bad. I don't want that as a plus anymore. I don't want this to be a sum. I want it to be a product of a series of things that I can then solve for. This is why we talked about factoring things out. If we look at these two individual terms, here's the first term, here's the second term. What do those terms have in common?
X plus 7 and x minus 8.
Good. So they both have an x plus 7 involved, so I'm going to factor out an x plus 7, and I'm going to factor out an x minus 8. And then in the bracket here will be all the gunk I have left behind. So the crucial question is, what power of x plus 7 do I want to factor out? To the first, right? Because remember what I've said, you always take the lower power, or the more negative power. And then what power of x minus 8 do I pull out? Negative 2/3. Okay, good. So if I pull an x plus 7 out of the first term, I'm left with a 2. If I pull an x minus 8 to the negative 2/3 out, when you factor out, you divide the exponents. So, or sorry, you subtract the exponents. 1/3 minus negative 2/3 is just going to be x minus 8. Okay, so that's what's left from the first term. Plus, I took one of the x plus 7s out of there, and this whole, then I got a 1/3, and then I took the whole x minus 8 to the negative 2/3 out in front. Now that makes me happy. Why does that make me happy? Because I then took something that was a sum and turned it into a product of three different things. And if those three different things multiply together to give you 0, what do you then know? It already is. I understand.
Actually, the 1/3 x plus 7.
The 1/3 came from here.
You just put it behind.
When I took the derivative, yeah, I just moved it in the back. Because of this whole thing, the x minus 8 went away. Okay. Two things multiply together to give you 0. What do you know about each of the two things? One of them has to equal 0. Three things multiply together to equal 0. What does that tell you about the three things? One have to equal 0. We don't know which one, so then we go and say x plus 7 is equal to 0. X minus 8 raised to the negative 2/3 is equal to 0. And that monster, 2x minus 16 plus 1/3 x plus 7/3 is equal to 0. The last one's the bad one. What about the first one? X equals negative 7. Second one, 8. Third one, you could multiply everything by 3 if you don't like denominators. You want to do it that way?
What I'm saying, did you distribute the 2 and distribute the 1/3?
I did, all right. That's how I got this.
Oh.
Okay. So depending on how you want to solve this, depending on whether or not you like fractions, I don't. So I would multiply this whole monster by 3 and get 6x minus 48 plus x plus 7 equals 0, because 0 times 3 is 0, and then solve that. 7x.
Excuse the interruption. Will J.D. Jones please report to your party at door 6? J.D. Jones, please report to your party at door 6. Thank you.
Sounds like we're seating for Olive Garden. I don't know who they are. Suits?
Yeah.
They were in suits?
Yeah.
Stay away from the suits. What do we got here? That's negative 41, so 41, so x, I hope I did this right, is 41/7. Okay, so my critical numbers then become, what, did I screw up somewhere?
No, never mind. I did my. Wait.
7,
No.
40.
Yeah, you're good. I'm thinking out loud.
Oh, well, no, no, I'm good, right?
Yeah.
Okay, all right, so my critical numbers then are, what do we say, negative 7, 8, and 41/7.
How is it 8? Does it make sense? Yeah.
What makes that equal to 0?
Um,
Yeah, I don't care about the negative 2/3, I just want to make that thing equal to 0.
You said one of them had to equal 0.
Yeah, we don't know which one, so we set them all equal to 0. Okay. Now what does that mean about those 3 points? Well, those points might be relative maxima, they might be relative minima, they might be absolute maxima, they might be absolute minima, they might be none of the above, they might just be special points. Okay. We don't care, because in this problem all we're looking for is the critical numbers. Okay, and by the way, that's about as bad as it gets. If you can do that, you'll be good with everything else, because more than likely you're going to see more problems like the one we did previously. We got them all? Yep, good.
Ooh, that was good. I like this.
Who are
too.
them?
Is that a Nissan Maxima?
I don't understand that it's in Nissan.
It's a Maxima.
Relative maxima.
Relative
Oh.
maxima. I'm really proud of this, kids. Thanks.
I think
Thanks.
it's a relative.
Well, it's a family, so they're all. It's not creepy maxima. It's relative maxima.
Confetti was the best transition.
Yeah.
30, I don't know what numbers they are.
Is there no